Hi there, my name's Heath. This is section 12.3, the dot product. Let's get started. When we talk about the dot product of two vectors, we are calculating a scalar from these two vectors that helps us calculate the angle between A and B. It gives a scalar for an answer that we can use to find the angle. To find the dot product of two vectors, we multiply matching components and then add the results. So we'll multiply the x coordinates together, then we multiply the y coordinates together, and then we multiply the z coordinates together, and we add them all up and get a grand total. This is what we're doing here. So if I want to find the dot product of these two vectors, we call it the dot product, and we write a dot between the two vectors to indicate that that's what we're doing. We take the 2 and the 3 and multiply them together. That's the 2 from this vector and the 3 from this vector. Then we take the 3 and the -4 from the vectors and multiply them together. And then finally we take the 2 and the 1 from the vectors and add them together. So the x coordinates get multiplied together, the y coordinates get multiplied together, the z coordinates get multiplied together. And this gives us 6 and -12 and +2. And when we add all those together, we get a grand total of -4. That's how we calculate a dot product. Let's try another one. In this case, A is the vector 3, 2, -1. And B is the vector 4j and +k, 1k, and no I, so there's a 0 in the x direction. Compute A dot B, not A plus B, A dot B, the dot product. And so we'll group the 3 and the 0 together. And we'll group the 2 and the 4 together. And we'll group the -1 and the +1 together. And we end up with 0 plus 8 plus -1. It gives us a grand total of 7. So let's talk for a moment about what this 7 actually tells us. It does give us some information. If the dot product of two vectors is positive, the vectors form an acute angle. So anytime the angle between the vectors is less than 90 degrees, the dot product is positive. And if the dot product of two vectors is negative, the vectors form an obtuse angle. So for angles that are greater than 90 degrees, the dot product is negative. And if the dot product of two vectors is exactly 0, the vectors form a right angle. Well, we know some other function that behaves this way, that's positive in quadrant 1 and that's negative in quadrant 2. Cosine also behaves that way. And I would like to be able to tell you that the dot product and the cosine were the same thing. But they're not. They're almost the same thing. And the problem is units. If I have a vector, or a pair of vectors, A and B, and I am measuring these vectors in meters, so that, for example, if A is equal to 1, 2, 7, and B is equal to 2, -5, 3, well, these represent how many meters they have moved in the x direction or y direction. And so when I multiply these together, I'm taking 1 meter times 2 meters, and 2 meters times -5 meters, and 7 meters times 3 meters, and adding them together, and the dot product, its units are meters squared. But if I calculate a cosine, the cosine of an angle is the adjacent side of a triangle divided by the hypotenuse of the triangle. And that's in meters over meters, so the meters cancel and the units are unitless. And so the dot product and the cosine are not quite the same because the units don't match. And so if we make the units match by canceling out the meters squared, the dot product is in meters squared, so we'll take out the number of meters in R, and we'll take out the number of meters in S. In this case, I'm using R and S for my vectors instead of A and B like I was up here. Then this cancels out the meters that are in the dot product, and now we have a unitless quantity on the right side and a unitless quantity on the left side. And now they match. And so as soon as we correct the unit problem, the dot product and the cosine turn out to be exactly the same. You will see this formula written in a large number of books this way, is the dot product is equal to the magnitude of R times the magnitude of S times the cosine, where the stuff that's on the denominator in this formula has moved to the left side of the equation in this formula. They're exactly the same formula, you just see it written in two different ways sometimes. I like to think of it this way, but if you have seen it before, written this way, and this is the way that's more comfortable to you, go ahead and use that formula. They're exactly the same. Okay? But the dot product and the cosine are identical to each other after a unit conversion has been made. And that's the important thing. We have to make that unit conversion. So let's try an example. A is the vector 1, 2, 2. B is the vector 1, negative 1, 1. Let's go ahead and sketch these for a moment. So A is 1 unit in the x direction. Two units in the y direction. And then from this point, we go up 2 units to get to 1, 2, 2. And it's this vector here, starting the origin and then to get 1, 2, 2. And then B is a vector that goes 1 unit in the x direction, 1 unit in the y direction, and goes down 1 unit from that point. So I went 1, positive 1. I misread where the negative sign was. 1 unit in the x direction, negative 1 unit in the y direction, and then positive 1 unit up into z direction. Let's try that. And so the thing that we're looking for is, what do we know about this angle here between this vector and this vector? That's what we're trying to calculate. Well, we know what the dot product is. The dot product of A and B is we multiply the 1's together, then we multiply the 2 and the negative 1, and then we multiply the 2 and the positive 1. And 1 and negative 2 and positive 2 is 1. Then we calculate the magnitude of the two vectors. The magnitude of A is the square root of 1 squared plus 2 squared plus 2 squared. And that's equal to the square root of 9, which is 3. And then we calculate B, the magnitude of B, which is the square root of 1 squared plus negative 1 squared plus 1 squared. And that's the square root of 3, which doesn't simplify. All right. So again, the cosine of the angle is equal to the dot product, except that we then have to convert the units by dividing by meters. And actually, we have to divide by meters squared, the meters in A and the meters in B. And so that's 1 over 3 times the square root of 3. So we can do that calculation. 3 times the square root of 3 is equal to 5.19. Something 1 over that is approximately 0.192. So I'll say this is approximately 0.192. And then the angle will be the inverse cosine of that. And we can calculate that out also. And we get about 78.9 degrees. All right. So that's how we calculate the angle between a pair of vectors. Find their dot product. That's usually a simple calculation. Find the two magnitudes. That's just using a distance formula twice. Dividing that out and using a calculator to calculate the inverse cosine. But we never have to draw a right triangle or do any kind of work with trig at that point. Okay? So let's go on to the next slide. Suppose that we know the magnitudes of the vectors and we know what the angle is. Find the dot product. So we're using the same formula from the previous slide, that the cosine of the angle is equal to the dot product after we divide out the units. But in this case, what we know is the angle. We don't know what the dot product is. And so we know that the angle is 30 degrees. And the magnitudes are 9 and 4. So the denominator is going to be 36. 9 times 4. And so we should be able to figure out what the dot product is. The cosine of 30 is the square root of 3 over 2. And so we'll multiply both sides by 36. The 36's cancel on this side, and they leave 18 on this side. And so the dot product of A and B is exactly 18 times the square root of 3. We're just using the angle to find the dot product instead of using the dot product to find the angle. All right. So let's move on. A couple of definitions. We say that two vectors are parallel if there is a constant k such that v is equal to k times w, or w is equal to k times v. And this definition applies as long as both vectors are non-zero. Two non-zero vectors are orthogonal. I want to talk about this word in a moment. If the dot product of the two vectors is 0. So if I calculate the dot product and I get 0, the vectors are orthogonal. And the 0 vector is defined to be both parallel and orthogonal to all other vectors. We can't always use this definition with the 0 vector, but it satisfies the definition. There's a reason why we saw orthogonal and not perpendicular. So why not perpendicular? So in 2 dimensions, two vectors that were not parallel to each other would eventually cross, and then if they crossed at a right angle, they were perpendicular. And so their directions were at right angles to each other. In 3 dimensions, there's a third possibility that could happen. We could have two vectors that cross each other and form a right angle where they cross, but we could have vectors that point in perpendicular directions, but they don't cross each other. Instead of the second vector going through this vector, the second vector might be, higher up on the z direction. And that these two vectors, they point in directions that are at right angles to each other, like this one points due north and this one points due east, for example. But they never cross. And the word perpendicular refers to intersecting lines. This refers to directions that may or may not intersect. So that's why we don't use the word perpendicular. These may not intersect. But they're still pointing in directions that were 90 degrees apart from each other. So, orthogonal is a weaker word than perpendicular because it does not guarantee a point of intersection. Apart from that, they really do mean the same thing in terms of the directions. The directions are 90 degrees separated from each other. But perpendicular guarantees an intersection point and orthogonal does not. Okay? All right. So let's look at this example. Let's determine whether these vectors are parallel or orthogonal or neither. So the first pair of vectors, I'm going to write these out as coordinate triples. -9, +3, +6. And the second vector is 6, -2, and +4. And they are not exact multiples of each other because this vector, this coordinate, this 6 and this 9 have opposite signs. And these coordinates have opposite signs, but these coordinates have the same sign. And if they had a common multiple between them, that multiplier could not be positive because it causes A and B to change signs for the x-coordinate, but it couldn't be negative either because the z-coordinate doesn't change signs. And so there is no common multiplier. And so they are not parallel. So let's say if their dot product is 0. The dot product of A and B will be -54 plus -6 plus +24. I'm multiplying the x-coordinates and the y-coordinates and the z-coordinates together. And, what is that? That is -36, but it's not equal to 0. And so these are not perpendicular either. And so these two vectors are neither. So then let's look at the two vectors in part B. A is 3, 1, -1 and 3. And B is 5, 9, and -2. All right, again, there's not a common multiplier because the z-coordinate changes signs, but the x-coordinate does not. If there were a common multiplier, it couldn't be positive because a positive number wouldn't cause a sign change here, but it couldn't be negative because a negative number would cause a sign change here. And so there's no common multiplier. And so these are not parallel. So let's see what their dot product is. The dot product is 15, that's 3 times 5, plus negative 9. That's negative 1 times 9. And then negative 6, which is 3 times negative 2. That's a 6. And 15 and negative 9 and 6 adds up to 0. And so these vectors are orthogonal. And up here, I should have also said orthogonal. I was talking about perpendicular on the last slide, and botched that up on the next slide. So these two vectors are orthogonal, but the first two vectors are neither. All right, let's move on. Suppose that we had a line L. This is L, but it's a little hard to see, but it's this line right here. And we have a vector V. And imagine that we also have some sort of bright energy source that is directly over V and casts a shadow. I'm trying to see I can't see it with the yellow. There you go. That forms perpendicular sides here with L. The shadow that V has cast on the flat surface L is called the projection of V onto L, and it's written with sort of this symbol. It's the projection of V onto L, and L is a little subscript in here. It's the vector line L that represents the shadow of V. If we want to be very specific and precise about it, we connect the head and the tail of the vector V to the line L using perpendicular lines. I can say perpendicular here because they intersect. And the projection is a part of line L that's cut off there. L and projection L always share the same direction because the projection of L is actually part of L, so they are obviously pointing the same direction. And so sometimes we're just concerned with the magnitude of projection of L. How long is the piece that's cut off? We just want to know how much length has been drawn here. If all we want to know is the magnitude, that's called the scalar projection. And it's written the same way, except instead of saying projection, we write COMP, which stands for component. We can say, we can call this the component of V projected onto L, or the component projection of V onto L, but that's where this term came from. We have formulas for both of these. The scalar projection is simpler to compute. It's the dot product over a single length. If we figure out what's going on with the units there, the dot product we've seen is in units of length squared, for example, meters squared. And then when we divide by just 1 meter instead of by both units, then we still have a unit of length left. And so this is measuring length. It is telling us how long that projection will be. It's giving us a length, and it's exactly what we want. And it's part of the formula for the projection. If we take that length and we multiply it by a unit vector, a vector that's 1 unit long, then we get a vector that is this number of units long. But we make a unit vector by taking a vector and dividing out its length. We did that in the last lesson. And so this is a unit vector. And so when we multiply the unit vector by the amount of meters that we have calculated in the projection, then we get a vector that's the correct number of meters long. That's the idea. So let's try a couple of problems using these two formulas. Okay? So there's a typo here. This should be a B. Let A be negative 304 and B equal the vector 729. And we want to compute a scalar projection of B onto A. So we were projecting B onto A. A is the thing being projected onto. It's a little smaller than the vector. And the formula for this is the dot product of both vectors divided by the magnitude of the vector being projected onto. Okay? So the dot product we can calculate. It's negative 3 times 7 is negative 21. 0 times 2 is 0. And 4 times 9 is 36. And the magnitude of A, you might already recognize there's a 3, 4, 5 triangle here. But I'll write it out as the square root of negative 3 squared plus 0 squared plus 4 squared. And that's on the top we get 15. On the bottom this is 5, and 15 divided by 5 is 3. And so whatever unit of length we're dealing with here, that's how long the scalar projection will be. It'll be 3 meters or 3 feet or 3 miles long, depending on what my units are. All right, if we want to compute the scalar projection of B onto A, I want to take the vector A and scale it so that it is now 3 units long. That's the idea. So, you know what I did? The scalar projection doesn't have this as its abbreviation. The scalar projection is component, not projection. I did that by mistake. I'm so sorry. Let's move on. This is actually projection, and it is the component part multiplied by a unit vector. So we've already calculated the first part. The first part is 3. The second part is A divided by the magnitude of A. Well, we've already computed the magnitude of A. It's 5 units long. And so we're taking 3/5 of this vector A. So 3 times negative 3 over 5 is negative 9/5. 3 times 0 over 5 is still 0. And 3 times 4 over 5 is 12 over 5. And that is the vector projection of B onto A. All right. Well, let's move on. Work done by oblique forces. By oblique, we mean that we may be not necessarily using the force as efficiently as possible. For example, I might be trying to slide a box along a platform, but I'm not applying the force exactly in parallel to the platform. I might be pushing down a little bit on a box, and so some of my force is being wasted because I'm not pushing it in the most efficient direction. That's the idea here, that we are not doing the work as efficiently as possible here. If we cause a force of F causes the object to move along a straight path, D, even if F and D are not exactly lined up with each other, the work done by that force is equal to the dot product of F and D. And because these will have an angle, there will be a cosine involved in this dot product, which will reduce the magnitude of F and D by the value of the cosine. That's the idea. F and D are vectors, but W is a scalar because it's a dot product. If our force is measured in newtons and our distance is measured in meters, then the work has the units Newton meters. And we have a name for that. A Newton meter is called a joule. And so we can write capital J as the abbreviation for a Newton meter. Okay? So let's try a couple of examples and then we will wrap up today. So let's find the work done by a force that moves an object from the point 0, 10, 4 to the point 4, 14, 22 along a straight line. The distance is measured in meters and the force is given in newtons. Okay? So the work is equal to the dot product of the force with the distance. The force is 8, -4, and 7. And the distance that it moved is the difference between these 2 points. In the x-coordinate, it went from 0 to 4. That's 4 units. In the y direction, it went from 10 to 14. That's also 4 units. And in the z direction, it went from 4 to 22, which is 18 units. And so when we multiply these together, 8 times 4 is 32. -4 times 4 is -16. And 7 times 18 is 126. And when we add all these together, we get 142. The force is in newtons. The distance is in meters. And so we can also say 142 joules. All right. So one more example. We are pulling a wagon by grabbing the handle and pulling on the handle with 14 newtons of force. And so we're not pulling directly in the line that we're working. We're pulling at an angle that's sort of convenient so we don't have to crouch down to the ground. But this isn't the most efficient way of dragging the wagon. We've pulled the wagon forward by 10 meters. How much work was performed? So we need to figure out what the force vector is. And we know the magnitude is 14. And we know the angle is 40. And so the coordinates are 14 times the cosine of 40 degrees. And 14 times the sine of 40 degrees. And we can calculate that out. 40 degrees, take the cosine and multiply by 14. And that's approximately 10.72. So I'll make this approximately. And then the y-coordinate is 14 times the sine of 40 degrees. So 40 degrees sine times 14. Is, oh gosh, so close to 9, I'm just going to say 9. All right. And then we calculate the distance vector. Well, that's just 10 meters in the x direction. So that's just 10, 0. And so the work that was performed is the x components multiplied by each other. 10.72 times 10 is 107.2 plus 9 times 0, which is 107.2. And again, the units are newtons for force and meters for for distance, and so this is 107.2 joules of work that was performed. All right. Thanks for watching. Have a fantastic weekend. I will see some of you in person on Monday, and stay safe. You take care.